In Chapter 14, we're going to look at multiple integration, starting with Section 14.1, which is about iterated integrals and also area in the plane. Similar to how we differentiated functions of several variables with respect to one variable when we were doing the partials, we can also integrate functions of several variables by a similar procedure. For example, let's consider the partial derivative. The partial of f with respect to x equals to 2xy. If we wanted to recover the original function f up to a constant, we would want to undo a partial derivative with respect to x. So we could think of the y term as being constant and integrate this function with respect to x. F of x comma y is going to be equal to the antiderivative of the partial of f with respect to x dx. This is going to be the antiderivative of 2xy dx. And this is where the dx becomes very important. This integration that we're doing is with respect to the x variable, which means that we can think of the y term as being constant. So this would be equal to, I can factor out not only the 2, but also the y from the integral, because with respect to the x variable, those things would be considered constant. So we get 2y times antiderivative of x dx. Well, we know that the antiderivative of x is x squared over 2 from the general power rule. The 2's would cancel, and we would get x squared y. Okay. Not only do we get x squared y, but something you should remember from Calc 1 and 2 is that whenever you do an antiderivative or an indefinite integral, we get a constant of integration. In this case, the constant of integration itself is going to be a function of the other variable, since any expression that contained just y's and constants, when differentiated with respect to x, would have produced a value of 0. We can also use a similar type of procedure in the fundamental theorem of calculus to evaluate definite integrals of this type. The antiderivative of 2xy with respect to the x variable we saw was x squared y, and you could then evaluate this antiderivative in the x variable with an upper limit of 2y and a lower limit of 1. The fundamental theorem of calculus says you would substitute in the upper limit of integration into your variable. So everywhere we see an x, we would put 2y. So it's going to be 2y squared times y. And then subtract that function evaluated at the lower limit of integration. That would be replacing the x with 1, and we get 1 squared y, which would produce 4y cubed minus y. Similarly, we could also have integrated with respect to the y variable by holding and thinking of the x variable as being a constant. Something that will become very important throughout this section, and we'll see this, that whenever you're integrating, you can have variable bounds like what we kind of did here. Notice that my variable bounds were from 1 to 2y, which is perfectly fine because the integration was done with respect to the x variable. The one thing that we cannot ever have is be integrating with respect to one variable and also have the limits of integration be in terms of that variable. So an expression like the definite integral from 0 to x of y dx, that wouldn't make sense because the variable of integration is x because it's dx, but then you would also have an x as a part of one of the limits of integration, so that wouldn't be defined. Let's take a look at example 1 together. We want to evaluate the definite integral from 1 to x of 2xy plus 3y squared dy. So we're doing a definite integral here with respect to the y variable. If we're going to integrate with respect to y, then we're going to think of x as being constant. So when I integrate this first term, the 2x is constant, so leave the 2x alone. The antiderivative of y with respect to y would be y squared over 2 plus the antiderivative of 3y squared with respect to y. That would be y cubed, and then this is going to be evaluated from 1 to x. Notice that these two cancel, the 2's cancel, so it's just going to be x y squared plus y cubed with an evaluation going from 1 to x. Remember, we integrated with respect to the y, so we're going to substitute these limits into the y variable. So everywhere we see a y, I'm going to put the upper limit, or the upper bound of integration. That's going to be x times x squared plus x cubed, and then subtract what we would get if we plugged in the lower limit of integration in for y. That's going to be x times 1 squared plus 1 cubed. This will give us x cubed plus x cubed minus x plus 1. And if we simplify this, that's going to give us 2x cubed minus x minus 1.